We're going to do concavity and points of inflection. Okay? This is essentially the last thing we really need to know in terms of sketching graphs. When we talk about concavity, we're talking about concave up and concave down. These first two are examples of concave up. And our bottom two are examples of concave down. Now, one way we could tell this, because it could sometimes be hard looking at a graph, especially if it starts to make almost like an S shape like this. Well, when does it turn concave up and when does it turn concave down? What you can think of as the tangent lines. For concave up, you'll notice the tangent lines are always below the curve. Okay? All of our tangent lines fall below. For concave down, all of our tangent lines fall above the curve. Okay? So that's how we know something's concave down or something's concave up. And it'll help us when drawing, because we're going to get points when it changes from concave down to concave up. Okay? Those are going to be called inflection points. We got that information so far. So concave down, concave up. We know what our local minimum and maximum is. I'm just going to touch on it briefly. The lowest point, local minimum. Highest point, local maximum. Okay? Now we're going to talk about how we find this information. Okay, so we've talked about the theory of what concavity is. In order to find this type of stuff, we need to use our second derivative. We're used to using second derivatives when we're talking about speed, velocity, and specifically acceleration. To find acceleration, we're going to talk about how second derivatives or higher order derivatives help us in terms of graph sketching. So we're going to go to another page, and we're going to get an equation here. Okay. Now remember, we've done a lot of stuff with equations so far. One thing says to sketch our graph here. We're going to try to do our best of it. We have our graph of y is equal to x cubed minus 3x squared minus 9x plus 10. Okay. Now we got to talk about how these things are going to help us. I'm going to write a couple rules above. First of all, if f double prime, so second derivative of x, is larger than 0, so numbers we put in, that means we're concave up. Should probably put that on the other page, but it's fine. If f at x is less than 0, we're concave down. And if f of x is equal to 0 and changes directions, we have an inflection. Okay? This is a point of inflection. We'll also talk about local minimums and maximums after that. Okay? But these are some important rules we need to know. They've given us this graph. Now we know there's many things we can do. We can find vertical asymptotes if there are any. We can find horizontal asymptotes if there are any. This is not a rational function, but a polynomial, so we probably don't have either of those. We can also find if it's heading in a direction up or down, or what critical values are by the derivative. So we've learned a lot about graphing. This is our last step. What we're going to do is first we're going to derive this function. And in order to get to a second derivative, well, we have to derive it a first time. So y prime is 3x squared minus 6x minus 9. Okay? Which then makes y double prime, or the higher order derivative of this. They put it in Leibniz function or function notation, or you can put it like this. We have 6x minus 6. Okay? So that's our higher order derivative, our second derivative to this. What we're trying to find is a point along this when we would have, if something's going to be concave up or down. Now, concave up and down usually happens around critical values. Okay? And critical values we find using our first order derivative. So what we're going to do here is, first of all, we are going to find concave up and down, and if there's an inflection point. To find an inflection point, remember that's when our f double prime x is equal to 0. So we're going to plug 0 in for y double prime here. We get x minus 6. 6 equals x. X equals 1. So x is equal to 1 when f double prime x is equal to 0. X is equal to 1. So what that means is we might find an inflection point at 1. But we have to prove that it can be done. And what I mean by that is we need to find the values when x is less than 1 and when x is greater than 1. We already know when x is equal to 1, our f double prime x is equal to 0. So that's good. Okay, you can almost make a chart out of this. When our f double prime is less than 1, okay, what's our value going to be? And that's when we get into our greater than 0, concave up, less than 0, concave down. So we're going to take a value less than 1. Let's say we use the value of 0. Okay. So we're going to find f double prime when x is 0. Well, that gives us 6 times 0 minus 6. We get negative 6. Which means our f double prime of x when x is less than 1 is less than 0. Which means if we're less than 0, we're concave which way? Down. Okay? Concave down. In other words, something like this. Our other option is when we're greater than 1. So let's find f double prime when we're at the number 2. That would give us 6, 2 minus 6. We're looking at 12 minus 6. Positive value. Very important. F double prime x is greater than 0, which means we are concave which way? Up. Now this is why we checked both. Did we change directions at the point of 1? Did we go from concave down to concave up? Anyone? Yes, we did. So yes, we changed directions. Yes, changed direction. Therefore, we have a point of inflection. And in other words, what's kind of happening, if we could draw that shape, it's like this. At this point here, we've changed from being concave down. We used blue, I think, when I did concave down. This was concave down, remember our tangents. It then changed at that point of inflection, at 1. It then changed to concave up. Our tangents are now outside of it. Okay? So we changed from concave down to concave up at that point of inflection. But there's something else we want to also look at. Remember I talked about it. It was our first derivative here. We do want to find critical values. And at critical values, we want to figure out if we're concave down or concave up, because then we can find local minimums and maximums through those. So let's jump to another page here. Okay. Our original function was y was equal to x cubed minus 3x squared minus 9x plus 10. Okay. We derived the function, so y prime, and we got 3x squared minus 6x minus 9. And then our double derivative of the function was 6x minus 6. Great. Critical points. Critical points are important, and we're going to put a couple rules above with them. Okay? If f prime c, and c stands for critical point, is equal to 0, so we put it into our first derivative. If it equals 0, and if f double prime at c is greater than 0, we have a local minimum. That's our first if. If f prime c, being that critical point, so our derivative is equal to 0, and our double prime at c is less than 0, we have a local maximum. Now, there is an option where this will be equal to 0 and this will be equal to 0. And in which case, we won't have local mins or max, we'll have extreme. If f double prime c is also equal to 0, okay, we'll have to find if it's concave up or down around it. But we either have an extreme min or an extreme max. Okay, they're not as common. So we're going to talk about just local ones for now. So we need to find our critical points, and to find critical points, we use our first derivative function. If you guys remember, that's when our tangents are 0. So we set it equal to 0. We look for 3x squared minus 6x minus 9. We're going to factor this. I can take 3 out. X squared minus 2x minus 3. Still equal to 0. This is going to give us 3. X minus 3. X plus 1. There's our factored form. Okay. So our critical values, though, we know the 3 won't become important. We're going to get x at 3 and x at -1 are critical values. Okay. These are f at c's, f prime c, and this is another f prime c. Well, remember, at these points, we need to figure out if it's concave down or concave up in order to find local minimums or maximums. Luckily, we've already kind of done that part of the information on our other page. Remember, our point of inflection was at 1. So if our point of inflection is at less than 1, well, at less than 1, we're at -1. And when we were less than 1 on the other page, we were concave down. So in this case, that means our f prime prime of this c is less than 0. So local, if we're less than 0, what are we? A local max. Okay. And at the other value, x was at 3. Well, that would be when x is greater than 1, and we already figured out it's concave up there. So what that means for f is f prime prime c at this point is greater than 0. So if we're greater than 0, we have a local what? Minimum. We have a local minimum. So let's try to piece this graphing information together. We have some critical points. Our critical points were at what? -1. So somewhere here, and 3. And we had a point of inflection at 1 itself. This was our point of inflection. Okay. Now, we don't know. I can plug values in to find them, but I'm not going to do that right now. We're just going to estimate. So if this is a critical value, what that means is this would be a turning point. So maybe we're decreasing, increasing. And remember, we said this was a local max. We did figure that out. And we know we're going to say this here is our local min. They're on the x values. This is when x was 1. This is when x was 3. We just figured that out. So we have a local max. So we go up and we know we're coming down. And we also know we have a local min here, so we're coming up. What's important is our 1. We have a point of inflection. So what that means, it goes from being curved like this to curved like that. Oh, that's not that great. Let's try that again. I'm going to try it a little more pronounced. Okay? I made that a little more pronounced because what happened, remember, we changed directions of our tangents. Our tangents went from being concave up before that point of inflection to being concave down after that point of inflection. Okay? So now our curves were concave down, and we had our local mins and max. Now we could have plugged in and found out the actual correct values. This is just a rough sketch of something like that. Sorry, around the y-axis it's hard to see. But that was our rough sketch with the information we have found.